A very good morning. A very good morning to everyone, and welcome to the concluding day of the International Year of Quantum Science and Technology. We begin day 6 with the second lecture in the insightful series on designer quantum materials delivered by Dr. Debakanta Samal. As a leading experimental condensed matter physicist and reader F at the Institute of Physics Bhubaneswar, Dr. Samal has made remarkable contribution in quantum materials, particularly in atomic layer engineering of heterostructure and oxide thin films. In today's session, he will delve deeper into topics such as emergent phases in quantum heterostructure, exotic superconductivity in artificial oxide systems, magnetic frustrations, and orbital engineering in low-dimensional systems. Please join me in welcoming Dr. Debakanta Samal for Lecture 2 on Designer Quantum Materials. Sir, the platform is all yours.
Okay, so can you see now?
Yes, sir.
Okay, if I make full screen because I do not want to have problem. Is the slide is moving?
No, sir.
Okay, then like yesterday. So let me minimize it. Is now it is moving?
Yes, sir.
Okay, fine. So very good morning to all of you. I little bit start with what I was doing yesterday. Then I will go to a new topic. So this is what I was talking about, the magnetism. I talked about what is a paramagnet, how the time average magnetic moment becomes zero, and you have a net magnetization zero, and you have a ferromagnet. As I was taking for a particular spin of a ferromagnet, if you take snapshots, photograph, it will not change. It will not fluctuate. So that's why the time average magnetic moment is not equal to zero. And for a ferromagnet, we know that there is a net magnetization. So magnetization is not zero. But for an antiferromagnet, similar to ferromagnet, the time average magnetic moment at a particular site is not equal to zero. But the overall magnetization is zero because it is antiferromagnet. You have equal number of upspin and equal number of downspins. So this is what I was talking about. And I told you that to understand this paramagnetic to ferromagnetic phase transition, you need to consider this symmetry breaking aspects where paramagnetic is a disordered phase and ferromagnetic is an ordered phase, and where the theorem tells that if there is a phase transition, in most of the cases there will be a symmetry breaking. For example, when there is a phase transition from paramagnetic to ferromagnet, very simply one can tell that the spin rotational symmetry breaks. Similarly, from when you go from liquid to ice, there is some symmetry must be breaking there. What I was talking yesterday is as we are working on this layered materials, one layer or two layer materials. I was talking about this very famous theorem, Mermin-Wagner theorem, which tells that if you have a two-dimensional lattice, that means atoms are in a two-dimensional, like consider that as if you have a paper where atoms are sitting, and if you put the spins at each atom, because each atom has some spin, some electrons, some unpaired electrons are there at each atomic site, so it will give rise to spin. So if you put the Heisenberg spin means it has three components as I mentioned earlier. It is Sx, Sy, Sj, and what you will see that Mermin-Wagner theorem tells that for isotropic 2D isotropic Heisenberg system with short-range interaction means it is generally the exchange interaction, what we call the Heisenberg's exchange interaction, or any kind of exchange interaction. It's short range. It is strong, but it's short range. But you might be knowing also there is dipolar interaction. But dipolar interaction is a very long range interaction compared to exchange, but it is very weak. So what we are seeing, we are considering a two-dimensional lattice like a sheet of paper on which the atoms are sitting, and each atom there is a spin which is a Heisenberg spin. If this is the case, this theorem tells that you will not have any phase transition. So this is what you see here. in the 3. So there is a two-dimensional lattice, and spins are random spins are there, like Heisenberg spins Sx, Sy, Sz component. You see there is no magnetization, because we know that if there is a phase transition, as I showed you in the previous graph, if there is a phase transition, from you are coming from a degenerate phase to a ordered phase, so your magnetization will shoot up. It will increase. It will start at the critical point Tc, then it will increase. But you see here, the magnetization versus temperature curve is flat, absolutely zero. That means there is no phase transition for a 2D Heisenberg system. And similarly, I was talking about, now consider you have same two-dimensional lattice, but your spins are not Heisenberg. That means spins have no three components. They do not have three components Sx, Sy, Sz, but they lie in the plane. They have planar components like Sx and Sy. And here they show very, very interesting things. You see the magnetization is still zero, like a Heisenberg's case. But if you look at the susceptibility, there is a divergence. And this divergence indicates there is a phase transition. Some sort of phase transition is happening. And this is a kind of topological phase transition where the spins form vertex and anti-vertex. So this is kind of very interesting. XY model. So this is your 3 is your Heisenberg's model. This is your XY model. So XY model does not show any magnetization, but it shows susceptibility diverges. And that is the indication of some topological phase transition happening because of vertex and anti-vertex formation, which it will take one lecture to discuss about this. I will not get into this. But, and the last one case, you see here, again, same lattice. You have like one sheet of paper, one lattice. And here the spins that you are putting are only one component. They are like Ising spins, like they have either Sz or whatever, minus Sz, they have components. And now you see they have the phase transition. They have a clear phase transition here. So you can see here there is a magnetization and the susceptibility diverges at Tc. So this is what I'm talking about, a two-dimensional lattice where you have put in one case Heisenberg spin, in another case XY spin, in another case Ising spin. And I showed you that this is, sorry, just a minute. Yeah, I showed you that this Mermin-Wagner theorem prevents, there will be no occurrence of phase transition. But as I mentioned here, and this is what is your the first term in this Hamiltonian, what I've written here is your exchange interaction, Heisenberg's exchange interaction, Si.Sj. Forget about now the second part. Consider this Heisenberg's exchange interaction, and Mermin-Wagner theorem tells that if you have a Hamiltonian like this, only having the first term, which is the isotropic exchange interaction, then in 2 dimension or less than 2 dimension, they will not show any phase transition. But what you see here, there have been many examples in the recent days. Just in few years ago, people have made 2-dimensional lattice of various materials, starting from you see CRI3, these are various magnetic materials. What they see that even though you put them in 2-dimensional lattice, they show a phase transition, which kind of does not agree with the Mermin-Wagner theorem, which was telling that a 2-dimensional lattice with the isotropic Heisenberg exchange interaction will not show any magnetic ordering. But here we see that clear experimental evidence that is happening, that there is a phase transition, so there is a ferromagnetism is occurring. So why does it happen? No, because this kind of material, if you introduce anisotropy in your Hamiltonian, this is what the isotropic exchange interaction. This is your on-site, the second term in the Hamiltonian is your on-site anisotropy term. So if you put anisotropy, and then what people have found that it can show a kind of magnetic ordering. Why? The reason is why does not the isotropic Heisenberg exchange interaction does not show any ordering at finite temperature? Because there will be excitation of magnons, spin wave excitations that will kill the ordering. But when you put this kind of anisotropy in your Hamiltonian, or the system has some anisotropy, magnetic anisotropy, it could be on-site anisotropy or inter-site anisotropy, then it will be difficult for the spin excitations So that's why you can restore this magnetic ordering in a system, though it is a Heisenberg system, but if you have anisotropy, you can have that. So this is what the and if anybody wants to have a detailed derivation of magnetism in two dimension and Mormin-Wagner theorem, they can look into this. They can search by this very easily derived article by Frank Schreiber, and you can look at it if you want. You can do, and what it shows finally. This is what is the question: does a lower dimension, for example 2D instead of 3D, less neighboring spins change the ordering temperature? That was the question, and this was kind of the Mormin-Wagner theorem in PRL 1966, and they derive it. They find that this term delta mt, which is the change in the magnetization, that was kind of that diverges, so that the reduction in magnetization that diverges, so it does not show any kind of net magnetization. This is a very readable and understandable. If anybody is interested, can look into this article. This is what about if you have only one layer, you are putting either Heisenberg spin. But what happens if you have many layers and you are putting Heisenberg spins? So this is an example I have given. So this is known as a 2D Heisenberg. This is known as a 2D Heisenberg magnet. Now what you do, we call it, this is quasi 2D. Why quasi 2D? Here it is not only one layer, there are many layers. I have shown here two layers. So this layer is, one layer is magnetically active, another layer is magnetically active, but the separation between two layers is very large. So the spin cannot, the one spin in one layer and the other spin in the other layer, they couple with each other, but they couple very weakly, because you know the exchange interaction kind of gets weakened with the separation. The more the separation, the exchange interaction gets reduced. That is what we know. The exchange interaction is nothing. It comes from the orbital overlap, those kind of things it comes. So this is what is the kind of, the more is the separation. So here what you find, that is a strong exchange interaction in the plane. That is, we call it intraplane. But if you compare the exchange interaction between two layers, that is very weak. That means the intraplane exchange interaction is much, much larger than the interplane exchange interaction. So in this case, what you find, these are kind of known as this quasi 2D magnets. So one case I show you pure one layer, that is my previous slide, where they are talking about this Mormin-Wagner theorem. Now what I'm talking about, it is not a one layer. There are many layers are there, but they have very weak coupling between these two layers. And this kind of systems are quasi 2D Heisenberg magnets. And this is very important area of research. And how does the ordering happens in this kind of material? You see, at T greater than Tc, all spins are here randomly oriented. This is paramagnet. As you are cooling the temperature, the arrow that I marked at lowering of temperature, so in each layer, some ordering starts. This, you see, this was completely random paramagnet. Now, as you are cooling, there is some ordering starts here. Also, some ordering starts in the next plane. And now, what happens when you again you are cooling down the temperature? The coupling between this plane, the lower plane, and the higher, the bottom layer and the upper layer, that starts, and finally you will have a magnetic ordering. So this is how the quasi 2D Heisenberg's magnets. So I told you first the single layer or 2D magnetism. Now I discussed how does the quasi 2D magnetism, and this is the kind of very interesting area. And we have been working on various quasi 2D material and trying to understand the magnetism. And we find that in certain cases, only the Heisenberg's term here, you can see here, Jij.Sj is not sufficient in specific materials to explain the underlying magnetism. We need to incorporate some anisotropic exchange, which is another kind of exchange, which is DMI, Jolansky-Moria interaction. I'm not going into that, probably people who are not aware of it. But what I wanted to tell that there are systems where only in this kind of systems where this only Heisenberg's exchange cannot explain your magnetism. You need to consider some other interaction. For example, if you have a non-collinear magnetism, that means spins are, you can see here, the spins are not parallel. Everything is not parallel. They are non-collinear. So to understand this kind of a non-collinear magnetism, you need to consider in many cases this DMI. This is kind of the Hamiltonian. You can see here the second term is not very much similar to the exchange Heisenberg's exchange. Its form is like this: D dot Si cross Sj. So when you introduce this Hamiltonian, if your system has this Hamiltonian, this term, then it will show this non-collinear spin structure. And which kind of system will have the second term in the Hamiltonian? That is again kind of research point of view. We can discuss more that the system, the system should have break inversion symmetry. If it breaks inversion symmetry, then it can have this term, this is second term in your Hamiltonian. So this is kind of I gave a little bit idea about this. What is Mermin-Wagner theorem, 2D magnetism, what is quasi 2D magnetism. Now let us see now. I wanted to change my gear, but before that, to topological physics, I want to give one example of something before I go to there. So we are talking about the interface. That was yesterday, I was very much emphasizing the interface because I was telling that interface is the device. For any kind of device, you need to study the interface properties. So now, for a ferromagnet, if it is a kind of we know from our matriculation that for a ferromagnet, there is a hysteresis. So I have shown here that the hysteresis M versus H, this is a hysteresis. We know it, that ferromagnetic material, if you plot M versus H, they will show a hysteresis. Now I am asking a question. If you put a ferromagnet close to an antiferromagnet, what will happen? So for example, in the one, see the black spins are ferromagnet, and this is red one, let's say antiferromagnet. But somebody may ask why antiferromagnet spins are randomly oriented, because this is above the nil temperature. Now, if you consider this kind of system, a ferromagnet is in close proximity with an antiferromagnet, what you will see that, you see here, when this is your 1, this is your 2, you see when we have applied the field. So you see you have applied the field in positive direction, all spins are in this direction, ferromagnet spins and antiferromagnet is aligned. But now when you reverse the spin, because you need to measure the hysteresis, you need to come from first quadrant to second quadrant, then third quadrant, then fourth quadrant. That is what is the MH, hysteresis low. So now when you are retracing the field in the negative direction, you look at the 3, these ferromagnetic spins, they try to follow the field direction because they want to rotate along the direction of field. You are going from first quadrant to second quadrant, you are changing the field. So the ferromagnetic magnetic moments, they want to follow the field. But what happens at the interface, there is strong coupling between the antiferromagnet. The antiferromagnetic spin does not allow the ferromagnetic spins freely to go back into the field direction. So you require to apply more field in this kind of system. Had it been a simple ferromagnet, look at the first top hysteresis, the positive coercivity and the negative coercivity, they are same. But when you are making such measurement on a system, on a ferromagnetic system, which is coupled to an antiferromagnetic system, now what happens? Because of there is some interfacial interaction, the antiferromagnet is interacting with the ferromagnet at the interface. So the ferromagnetic spins are not freely moving with the magnetic field. Rather, they are experiencing kind of torque. So what does it mean? You require to apply more field in the negative direction to switch the ferromagnetic spins. Now you see, the hysteresis has completely shifted. It is not a symmetric hysteresis. You see, coercivity in the negative side is more, coercivity in the positive side is less. So you see an asymmetry in the hysteresis. The hysteresis is not symmetric around H equal to 0. There is asymmetry in the hysteresis. And this asymmetry is known as exchange bias. There is something called bias. Somebody is there which is biasing so that the hysteresis is going in one direction more and it is shifting in one direction. And this is a very important phenomena which has a lot of application in spintronics. we are using various kind of spintronics devices, starting from your this pen drive, laptop, various kind of things. And this exchange bias phenomena has a lot of application. So what is the important point of exchange bias? The hysteresis loop shifts in a particular direction. For ferromagnet, it will not do. Only simple ferromagnet or single ferromagnet, it will not do. But you are introducing an interfacial coupling between ferromagnet and antiferromagnet. You see how the manifestation is. The loop is shifting. And in this regard, we have done various work. I do not want to get into detail. You see here the hysteresis C, figure C, how the hysteresis is shifting from one to another. So this is a very important point to look into how this the hysteresis shifts in a ferromagnet, antiferromagnet. I'll give one more example to motivate you. With this, I will end this part and I'll go to the topology. So if you look at the periodic table in 3D transition metal, you have manganese, iron, cobalt, nickel, copper. This is what the periodic table you look at. And if you look at the manganese oxide, iron oxide, cobalt oxide, nickel oxide, they all form rock salt structure. The rock salt, the salt that we eat, table salt. The structure of all the oxides, manganese oxide, iron oxide, cobalt oxide, nickel oxide, it's similar to the crystal structure of the salt that we eat. You see, it is a very cubic structure, rock salt structure. But when you go to copper oxide, you see, it has got very distorted. It is not cubic, it is not rock salt, it is very different. So if you look at the Nil temperature, these are all antiferromagnets. This manganese oxide, iron oxide, cobalt oxide, nickel oxide, these are all antiferromagnets. If you look at their Nil temperature, you see Nil temperature manganese oxide is roughly more than 100, and iron oxide it is little close to 200, cobalt oxide it is like less than 400, like this. But when you come to this copper oxide, you see it is a linear trend increasing. As you're going from manganese, periodic table you see your first is manganese, then iron, then cobalt, then nickel, then comes copper. So somebody should expect that if it is just increasing with the periodic table elements, then one should get a point like this, the blue point, copper oxide. But what we find in actual experiment, copper oxide has a Nil temperature, magnetic ordinary temperature is much less compared to that plot, that graph, linear trend. So why does it? And it arises because the structure is different, because the exchange is different, the magnetic exchange interactions are different. Now the question I am asking, nature does not give you copper oxide, which is like rock salt, which is the left hand side. Nature gives you copper oxide, which is very distorted. It is not a symmetric structure. Now I'm asking, can we design artificially a copper oxide which will have a rock salt structure? And if we can design copper oxide which will have a rock salt structure, probably we can see maybe this line will be extrapolated. It will have a larger Nil temperature. So you can do this kind of things, and we have been successful making copper oxide rock salt structure. I'll not get into this. This is one of the students' work. He has been successful, and we looked into its magnetic properties, how to make it magnetic, and we are looking for how to make it superconductive. So my point is, you can design your material. If you have the idea what you want to study, you can design it even though nature does not give it. So with this, I think I will conclude the first part. I will now go to the second part. Let us see how much I can cover. Yeah. Any question up to now in the first part? Because this is what missing yesterday. All right. So now I will introduce little bit, as I mentioned, I will talk something about this topological materials. So
can I ask?
Yeah, please. Yeah, I can hear you.
Am I?
Please ask. Yes. Yeah.
Am
Yes,
I
sir.
audible? As you are telling, when there is a ferromagnetic 2D over which antiferromagnetic, and
Yeah.
we apply the reverse bias,
Right.
and the antiferro will influence the ferro, but why
Yeah.
not the reverse? Because ferro is a strong J value compared to antiferro.
Mhm.
So why the antiferro influence the ferro to follow the field direction, thereby leading to distorted uh, hysteresis?
Yeah.
Why not the reverse?
So there is already a antiferromagnet. If you look at the three,
Yeah, yeah,
there is already, you see, ferromagnets were all aligned along the positive x direction, let's say.
yeah, yeah.
But there is the antiferromagnetic coupling between
Okay,
this. So to break the antiferromagnetic coupling between two spins, it costs you more energy.
I see, I see. I
So
see.
what it
Thank
will
you.
do, it will slowly rotate the ferromagnet, but somehow it is kind of, there is a glue. This antiferromagnet, this coupling, it is not allowing it to go freely to the second quadrant.
Second quadrant.
So you require really to give more field to really flip
I
that
see.
chunk of ferromagnet spins to go into second quadrant.
Okay, sir. Get it. Thank you. Thank you.
Okay. So now I will get into this part. So we all know spinor bit interaction. And we know that it is a relativistic effect. We study it now, maybe we are studying at +2 or BSc, I don't know. Or maybe +2. Now I don't know whether people are taught at high school level, whatever. But this is what we know. The spinor bit interaction is a relativistic effect. And how do you understand it? Like you see here, if you look at the proton's point of view, the electron is moving and it is experiencing a magnetic field. That's what this is your proton point of view, and this is your electron point of view. If you look at, you will see it from electron point of view as if the nucleus is moving, a charged particle moving. So then you will experience a magnetic field. That magnetic field the electron experiences, and that is what the spin orbit interaction. This is a very qualitative understanding by changing the frame of reference, which frame you are looking at. This is the atomic spin orbit interaction. Similarly, if you consider a solid, there is not only one atom, there are many atoms which are placed. You can look at from like ions point of view, how the electron is moving. And if you look at the electron point of view, you will see as if the ions are moving. And this is effectively same as your atomic picture. You will get a spin orbit interaction. And the detail you can get it from any atomic physics book. I don't have to go into it. And the atomic spin orbit interaction scales with z to the power 4, roughly. There are some proportionality constant are there. That means the more the atomic number, the spin orbit interaction is more. The atomic spin orbit interaction. There are various other spin orbit interaction which I will not discuss here. So the atomic spin orbit interaction scales with the atomic number. The heavier is the atom, the spin orbit interaction strength is more. This is what we know from our standard, maybe first year quantum mechanics or this atomic physics books. You see here, and I was telling yesterday, I'm repeating this graph because this is very important graph. And this slide is from my professor with whom I was doing this right hand side. I was doing my postdoc. He was the director at Max Planck Institute, Stuttgart. This is one of his slide, the right hand side figure. So we know that the atomic spin orbit interaction varies with z to the 4. And I told you yesterday that how the correlation, the on-site Coulomb energy, U, the Hubbard U, that changes. And I told you that the 3D transition metals, I've shown you in the left-hand side figure, the orbital is very narrow, the orbital is more constrained in the space. So you get large U, Coulomb U. That means putting 2 electrons in the same orbital for a cobalt costs you more energy than putting 2 electrons in the orbital of a iridium, which is 5D, because the iridium orbital is extended more in space, spatially more extended. So if you put 2 electrons, they will not experience large Coulomb U, but the 3D they will experience large Coulomb. So there are two things I'm introducing. One is Coulomb U, on-site Coulomb U, which I little bit talked about yesterday. And now I'm introducing spin-orbit interaction, because I showed you a slide yesterday. If you want to understand a solid, the electronic phenomena or the magnetic phenomena, there are various energy scales associated with it. I showed you yesterday what are the various energy scales. You have exchange interaction, you have spin-orbit interaction, you have electron-electron interaction, electron-ion interaction, various kind of strain energy, various energy scales are there. And to really who wins over what, that determines actually what is the ground state of a material. So now you look at when you are coming from 3D to 4D to 5D, as I told, the Coulomb U decreases. You can see here the Coulomb U decreases when you are coming from iron to, let's say, platinum or iridium in 5D. But you see the spin-orbit coupling. What did I tell? That the spin-orbit coupling scale with Z, the more is the Z, Z to the power 4, more is the Z. So the spin-orbit coupling increases. So now if you see, if you go from 3D, from 4D, 5D, the atomic number is increasing as you are going from 3D to 5D. So you see the spin-orbit interaction scale, the atomic spin-orbit coupling, that increases as you with increase in Z. So if you want to do the physics of the 3D transition metals, let's say cuprates, high T superconductivity, manganites, cobaltates, you do not have to consider their spin-orbit interaction, because spin-orbit interaction is very small there. That will not alter the physics mostly. But if you want to do the physics of the 5D transition metal oxides, like iridates, I'll come into this. You see, the Coulomb energy is comparable to the spin-orbit interaction. Coulomb energy is the order of EV, and spin-orbit interaction also goes to roughly order of EV, 500 millielectron volt or something like that. So if you want to study the physics of these heavier elements, for example, iridates, or systems involving platinum, or systems involving osmium, you cannot trace the spin-orbit interaction, because their spin-orbit interaction is equally important as your Coulomb U that I wrote the Hamiltonian, Hubbard Hamiltonian, so I U Ni up, Ni down. So there are two competing energy scales. If you want to study the 5D transition metal based systems, there are two competing energy scales. One is Coulomb U, another is spin-orbit interaction. But if you want to study the 3D transition metal only, so you will not have that. You will have mostly the physics is governed by the Coulomb U or the correlation. So this is what let me show you. So I'll come into this. Sorry, there is a problem with my slides. I'm just doing it. Yeah. So this is a homework I am giving. This is a PRL 2017. I will not tell you the answers, but please read it or at least understand. People ask, where is the relativity? Relativity maybe it is a, you know, why does the gold looks yellow and silver looks silver? If you dig into it, really get to understand why silver is yellow. That's why it is expensive. Nothing more. It is made of some atoms, and gold is also made of some atoms, but only the color makes it very expensive. And I give you a kind of, I suggest you, please look into that. Why gold looks yellow? And you look into that. This is because of a relativistic effect. So many phenomena, you see, spin-orbit interaction, I will talk about many things about spin-orbit interaction in later slides. It is a relativistic effect. And we do it on a daily basis. We study what is the relativistic effect influences our electronic property. Similarly, if you understand why gold is gold, color is yellow, it is a relativistic effect. There is something called, I have written it here, atomic orbital contraction and expansion. So you will see how because of this atomic orbital expansion, how the gold electronic energy levels are different than silver, and that is why it looks gold. Gold looks yellow. So please look into that. Where is it? Where is the manifestation of relativistic effect on determining the color of a gold to be yellow? I just wanted to make it more curious that really relativistic effect makes the gold to look yellow. You can give Google also, you can find some of the answers, but here is a recent 2017 NISPRL, so they talk about this. So this is what is the golden mystery. People have been trying for many years to understand about this, but the reason is there. The origin lies with this relativistic effect. So now you see, I have now plotted. If you look at my second plot here, so I introduced two energy scales. One is U, another is lambda. Lambda is your spin orbit interaction, and U is your Coulomb U. And you see, I have plotted a y-axis U by T. What is T? T is your hopping energy, kinetic energy. And x-axis is lambda by T, spin orbit by T. You see, when lambda is small and U is small, this is your first phase. These are kind of simple metals or band insulators. I talked about what is band insulator yesterday. So when a lambda is small, U is small, these are simple metals like aluminum or various band insulators, silicon, germanium. So these are well understood. Now go to the mod insulator. Like cuprates, I was talking about cuprates, transition metal oxides, various are cobalt oxide. Yesterday I told that it should be a metal according to band structure, but because of correlation, it is an insulator. So they are what I told, because these are 3D transition metal, the U is large, so it gives rise to the Mottness, Mott physics come into picture, and they are Mott insulator. And that is, I told you, for 3D transition metal, lambda is very small, so you can trace it. So you see, the Mott insulator is mostly governed by the large U, U by T days. So this is also extensively studied, this region, because we have been studying transition metal oxide for last many years, decades. And we have studied this small lambda and small U, like silicon, germanium, aluminum, various things that has been studied. Now come to the large lambda, lambda by T, which is kind of this yellow color or brick color, large lambda, but small U. This is what started the research when maybe 15 years back, something like that, 20 years back, the topological insulator. So like bismuth-based compounds, where lambda is more, because I told you bismuth is heavier element. So lambda spin orbit interaction is more because spin orbit scales with the more is the atomic number. But bismuth is not a 3D. So U is very small, correlation is very small. So this is also has been studied for last many years, 20 years, this topological insulator, bismuth-based compounds. So we have studied the phase diagram close to origin. We have studied this topological insulator phase diagram extensively for over last many years. We have studied also Mott insulator, the physics of cuprates, high-test cuprates, manganites, and various transition metal oxides over many years. So what we are trying to do now, we are trying to study a region in the phase space. In the recent days, what is the research going on? Where, as I mentioned, both lambda, spin orbit interaction, and U, the correlation, they compete with each other. And that is the region which is, you can see here, this is the region where various new phases emerge. You have various new phases emerge because of the competition between spin orbit interaction and Coulomb U. You have various new topological phases, wild semi-metal, spin liquid, spin orbit Mott insulator, various kind of new phases. This emerges. I forgot to put the reference here. This is, I had taken this slide from Professor Trivedi. Uh, this is his slide. What I told basically, this is her slide I had taken from her. This is spinor bit coupling, lambda by W. W is nothing here at T, because you know W is bandwidth. Bandwidth depends upon the hopping. And this is correlation U by W. So you see, whatever I told, these are aluminum, silicon, this kind of material. These are high mod insulators. Like here scale is changed. This is U by T. This is here. This is lambda by T. So what I wanted to mention is that the materials, like what is marked here, osmides, iridates, where the spin orbit coupling competes with Coulomb repulsion or Coulomb U or this correlation. So those materials these days are becoming very, very important, and there are various new quantum phases emerge in those kind of materials. So this is what all about why we want to study systems where the spin orbit interaction plays a very vital role to explore some new quantum phases. For example, let me just give you one example here. We know Mott insulator. I told you what is Mott insulator yesterday. There is a new term came, spin orbit Mott insulator. What is that? You see, here these are three sister compounds. One is from 3D, one is from 4D, another is 5D. Cobalt is 3D, rhodium is 4D, iridium is 5D. So you see, Sr2COO4 is a metal. If it is a metal, cobalt is a metal, then what do you think? Then if you go to 4D and 5D, because the orbital will get more extended, as I mentioned, when it's going from 3D to 5D, the orbitals, the radial part of the orbital, so will get more extended. So one would naturally think that if the Sr2COO4 is a metal, then Sr2IRO4 will be metal or even more metallic character. Because the orbital is more extended, there will be large overlap. But what surprisingly it was found that it is an insulator. So that was a bit puzzling from band structure point of view, that why it is an insulator. Because here orbital is more extended, because it is a 5D orbital. So to understand it, why it is a kind of an insulator, you can only understand it if you introduce the spin orbit interaction. So I will not get into the details. These are the references PL paper, but what I'm trying to put a picture before you, that we started from a simple band insulator, which our conventional band structure explains us when a band is completely filled or empty, depending counting the number of electrons. And I introduced yesterday there is a Mott insulator, how the correlation plays a very big role. Even the band is half filled, but it can divide the band, open up a gap between the filled part and half filled, and the other is empty. So that's what it introduces, a Coulomb gap. And now I'm talking something just to motivate you, that it is not only the Coulomb U or the correlation in such materials where the correlation and the spin orbit interaction, correlation U and the spin orbit interaction, they compete with each other. It can give rise to many exciting phases. And one of them I tried to motivate you, that spin orbit Mott insulator. It is not only Mott insulator where correlation plays a role, but in this case, both spin orbit interaction and correlation plays a big role. So these are the kind of things you can do. And as I was mentioning you in this slide, this is a very important slide, the left-hand side. Now you see, because of this spin orbit interaction, I told you there are some topological phases. So what did I tell you? Why does the gold looks yellow? I've written here, if you read, you will understand more. There is atomic orbital contraction and expansion. It is a relativistic effect. Because the mass increases close to the nucleus. Give me 1 second. So this is, as the electron is close to the nucleus, the mass increases because of the relativistic effect. And that gives rise to this orbital contraction expansion scenario. You can look into this literature. And now what happens in a material, in a system? This is your band structure. One is valence band, one is conduction band. You can look at it. Band, this is this one. And what happens because of this relativistic effect? As I mentioned, the orbital contraction. So what happens? One of the band will lower in energy, and another may go up. So there will be overlap of these two bands because of the relativistic effect is first one. So relativistic effect, I'm trying to explain you what is this Dirac and Weil semi-metals based on the simple atomic picture, relativistic effect and spin-orbit interaction. Relativistic effect tells that there can be atomic orbital contraction and expansion. And if that is the case in a solid, it is possible that the two bands, which was one valence band and conduction band, because of the relativistic effect, the band can go down or up, and there can be overlapping of these two bands. And this is what I've shown in the left-hand side. This is first relativistic effect. Now what do you do? Because this kind of materials where you have heavier atoms, there is a spin-orbit interaction. Because I told you the spin-orbit interaction strength can be 500 milli-electron volt in this kind of heavier elements or 1 eV. But now when you switch in the spin-orbit interaction, this is like a perturbation. So what it will do, it will try to open up a gap. That is what in the upper case you see when you are switching on the spin-orbit interaction, you are getting a gap. There is a gap opening up. But certain materials are there where even though after switching on the spin-orbit interaction, you cannot open up the gap. The symmetry of this material, the crystalline symmetry of the material, that does not allow to open up a gap at certain points in K space in the Brillouin zone. So what you see in the below figure, even though you have switched on the spin-orbit interaction, you see the spin-orbit interaction has not been able to open up a gap across the Brillouin zone at certain point in the K space. They stay connected and they show a linear dispersion here. And this kind of material are known as Dirac and Weil semi-metals because these are three-dimensional dispersion. They show Kx, Ky, Kz. They are linear. And this is what Dirac and Weil. I come into more little bit about this. And in the up figure, you see there is an opening up gap when you switch on the spin-orbit interaction, but there could be some surface states, which is topological states. So this is what I was talking about, the topological states. You understood what is Dirac and Weil. I will show you one more slide. And I showed you that even though you switch on the spin-orbit interaction, there is a gap, but there could be the surface states. You see in the gap, these red ones are the surface states. So that connects the valence band and conduction band. So a topological insulator is insulating in the gap, in the bulk, but it is conducting on the surface. That is what is the surface state. So this is your topological insulator. So if you want to look into more carefully, see, this is a semiconductor, this is an insulator, the dotted one, red one, the red dot, this one is a red one, is a Fermi energy. You see, for a semiconductor and an insulator, the Fermi energy lies in the gap, so there will be no transport, there will be no excitations. It is a semiconductor and insulator. There are not nearby states. For a metal, as I told you, metal has a finite density of states at the Fermi level. So that means there are states available close to the Fermi energy. If you give a little bit excitation, the electrons can uncover those states. So, and a topological insulator, it is very much similar to in the bulk. It is very much similar to a semiconductor or insulator. But in the gap, there are some states. So this is what two lines they have crossed, they have drawn it there to show that those are the surface states, and that is the typical character of a kind of this topological insulator. And this is what you see. If you look at the resistivity versus temperature for a semiconductor and insulator, it goes like this, it increases, it diverges at T equal to 0. And you know for a metal, the resistance increases as you increase the temperature because of other scatterings you can have electron phonon scattering at high temperature, so that increases the resistance. And for a topological insulator, if you look at the resistance versus temperature, because the bulk is insulating, it shows the insulating stain or semiconducting stain, but at low temperature, the surface conduction dominates, so it kind of gets saturated. This is what is topological insulator. Now I talked about two distinct other classes of phases, which is Weil and Dirac. So in a Dirac, I told you that, as I mentioned, this is the picture. The bands kind of they overlap with each other. There is the inversion of bands. The bands are getting inverted, and you switch on the spin orbit interaction. So at certain point you cannot open up the gap. Certain points in the K space in the brilliant zone you cannot open up the gap, and those points can show a linear dispersion, and that is what is the typical the Dirac and Weil. What is the difference between Dirac and Weil? Here it is a fourfold degeneracy. Here you can remove the degeneracy. That is what is Weil. So it is a chiral. The Weil is a chiral. You have a positive chirality and negative chirality. This is like source and sink. But here in case of Dirac, you have fourfold degeneracy. So this is what is kind of you can tailor. I mean, you can look for their dispersion by doing some experiments like photoelectron spectroscopy, or you can do transport measurement to look at how these electrons which show this linear dispersion with having chirality, for example, in case of Weil semi-metal, how these electrons show different transport properties compared to your conventional or the parabolic electron. The electrons coming from a conventional parabolic band, you will see that they show very different transport properties. So that is what we have been doing. I'll not be able to go through it, but we have been using transport properties to really distinguish whether it is a Dirac and Weil semi-metal compared to a system where only the parabolic bands are there, that we typically study conventional metals. For example, this is the work I was doing long back. If you look at the band structure SR3PBO, this is your oxygen band, this is your PB band, and this is your strontium band. As I told, there will be overlapping of bands, and this is because of a relativistic effect. The same is the reason why gold looks yellow. Now what do? You switch on the spin orbit interaction because PB is here. PB is a heavier element. So it has certain spin orbit interaction we need to consider. So you see, when you consider spin orbit interaction, we are able to open up a gap at every point, but in the red arrow, you see, we are not able to open up a gap at this point because the symmetry of the crystal of SR3PPO, the crystalline symmetry, does not allow you to open up a gap at that particular point in the K space. And there, the dispersion is linear. So this was kind of one 3D Dirac semi-metal. We are working on it, and we proved it based on the transport measurement. I will not get, we published it in Nature Communication. And based on the transport measurement, I told you the transport properties of the electrons like Dirac electrons and Weil fermions is very different than your conventional parabolic, the electrons coming from a parabolic band. So there are some quantum effects. You can really look into it, that how the transport is different. And we could do this. If there are some questions, I will get into the details. There is something called quantum interference effect, linear MR, and there are many things are there. This is again, you can just to give a clear picture. This is from another group. This is copper 3 PDN, another material. Look at the band structure here. Down, left hand side down. You see, this is the energy versus K, E versus K. But if you dissect it, you see there are various bands which are close to the Fermi energy or cutting the Fermi energy. So there is a band left hand side, which is a parabolic band. But if you look at this, there is a point here between M and R points in the brilliant zone. You see the two bands are joining and they are kind of linear in dispersion. So by zooming into the band structure, you can actually look into whether this is one way of doing, because the band structure people who really see how the electrons are organized, by looking into that, we can really find out whether there is a topological phases is present on that. This band structure is nothing. Band structure is just like spaghetti. There are many noodles. You can think of noodles. This is what it is shown here in the top figure. These are like spaghettis. But at certain point in the K space, they behave very differently than many other points. So this is kind of a one Dirac's metal. This is what one group they have established that this behaves like a Dirac. So with this one, I've told you that there is something called, which is a high energy physics concept, but we are using it to probe our materials. There is something called chiral anomaly. To probe this kind of this wild fermions, as I mentioned, the wild has this chirality into business. They have helicity, this chirality business. So what happens? This is like, you see, there are two wild nodes. They have one chirality here. The K and S are in one same direction. Here they are in opposite direction. These are kind of source and sink, the chirality. And in a wild semi-metal, and how can you get a wild semi-metal from a Dirac? As I mentioned, Dirac has fourfold degeneracy, and you need to remove the degeneracy to get this wild. How can you do that? Either you break the trim-universal symmetry, you apply magnetic field or introduce magnetism, or you break the inversion symmetry. This is what we understand how to make remove the degeneracy in case of Dirac semi-metal. And this is what you see. There are two nodes with having one chiral. This is having another chiral. And this gives rise to a very unique transport properties. This is an anomaly. Why anomaly? Because your classical physics, it does not tell that. Because these are two different chirality, electrons should not flow from one to another. But what happens in this particular case, if you apply magnetic field and electric field in the same direction, you will see the current which is proportional to B dot E in some way. You will find a current, and that chiral current is proportional to the, you can see this is the expression, this is B square, B parallel square. Classically, you should not see any current because B and the E are in the same direction. There is no kind of Lorentz force or something like that. But because of this chiral anomaly, you see that the chiral current in case of wild semi-metal varies as B parallel square, the applied field square. And this is what in one of the Dirac material, one of my students who is now at Israel, so he showed that the chiral conductivity varies with B parallel square. And this is well established in high energy physics, that the chiral current varies as B square. But here experimental we show that, yes, this is the case, indicating the wild character present in this material. I think there are many other things. I think I'll take some of the questions, but or I can just go, maybe this is my kind of. So as I mentioned, the iridates, because of iridates, why I'm emphasizing iridates in the last lecture, I was doing correlation because there I was talking about the U, about U much. Today I'm talking about more spin-orbit interaction because how that gives rise to this kind of new topological phases. So these pyropolar iridates, R2I, R2O7, they show various kind of novel phases. But unfortunately, what happens, to explore these novel phases, nature does not give the material, because you, as I mentioned, you need to break some symmetry, either inversion symmetry. So this, you can break these kind of things by designing the heterostructures or designing the layered materials. So, for example, this was product. This is a kind of a material U2IR2O7. This is again iridate because large spin-orbit interaction. It was predicted to be a wild semi-metal, but experimentally it was difficult to prove in the bulk because the property that we are looking for, that was getting cancelled out because of its cubic nature. So what we did, you can grow thin films, you can make these designer layered structures, and you can deviate from its bulk cubic structure, and you can actually address the kind of the topological phases in this. In fact, I will not get into that, but we established that this is a magnetic wild same metal. Let me tell you that wild same metal can be magnetic, it can be non-magnetic. There are many non-magnetic wild same metals, but magnetic wild same metals does not have a long list. So this is one of the material which belong to the magnetic wild same metal. So with this, what I wanted to tell you that if you can make the layered structure, that is what Feynman told in the 1915 lecture series. In lecture, what could we do with layered structure with just right layers? If you can make a right layers, if you have a rationale in your mind, this is what I want to do, but nature does not allow me. Nature gives in some different form. So if you can design your material, this quantum materials, then he asked, what could we do with a layered structure with just right layers? If you make right layers, you make right structures, you do not know, there could be some discovery. And this is what I would like to conclude. I will look for some questions. The design layer quantum materials, there is the exciting road ahead. You can have very exciting road ahead. You can have various kind of new emergent phenomena. You can really play with, control the phenomena by changing this the structure, by changing the interface, and that is the hope for the next generation quantum technology. Thank you very much for your attention. And I would like to thank some of the work that we have done, and this has been possible because of the funding from DAE, because ours is a organization which goes under the umbrella of Department of Atomic Energy. Also some funding from SERB India, and also I'm very thankful for getting this Max Planck Partner Group, and with which this Max Planck Institute Stuttgart I collaborate. So thank you very much for your attention, and I'll be happy for taking your questions.
So thank you, Dr. Samal. Thank you very much for sharing your invaluable insights and expertise with us today. Your thoughtful perspective had truly enriched our program and left us all inspired and better informed. We deeply appreciate the time and effort you took to be with us, and we hope to have the pleasure of engaging with you again in future events. Thank you once again for your contribution. So now we will open the floor for questions and
Samal,
answers.
yeah, before the question answer starts, I would like to formally thank Dr. Debakanta Samal for accepting our invitation and being a part of this event. Thank you so much.
Thank you, madam. Thank you.
You can
If
just
any,
now, yeah, the admin, anyone there? Anyone there?
Yes, ma'am. Yes.
Please put up the recording.